Hi, I'm Maurits Kaptein. I'm a professor of data science at the University of Tilburg and also one of the co-founders of Scailable. In this video, I'll explain why and how we build Scailable. So let's get started
by detailing why we started building Scailable as a solution for deploying AI and machine learning models. Really, this grew out of one of the research projects that some of us were involved in. So it's a relatively recent project in which we, based on a lot of data that was coming from the hospital, we're trying to predict different types of treatment for a specific type of cancer, colon cancer in this case. And after working through for over a year these types of models, we got to models that are reasonable and that at some point would be nice to incorporate back into the healthcare process. However, we found out that there is no clear, straightforward process of actually moving trained models that have been validated back into the healthcare process. And this problem of actually deploying machine learning models in demanding environments such as the hospital is actually what started our quest for thinking about this model deployment problem. And we actually found out that in a sense we're not the only one. There's many projects that don't make it from kind of training and validation stage to actually being deployed. And I think the bottom line there is just that it's extremely hard to deploy fitted models, even if those models are validated, even if pretty much everyone agrees that a specific AI or machine learning model has a purpose and its performance is on par. It's hard to move them from training to deployment. The move from training to deployment is hard for various reasons. One very obvious one being kind of conceptually this simple idea that where we often use data that's collected in some process, such as treatments in the hospital, for training a model, we often end up kind of removing that data from that process, cleaning it, then doing our model training, model validation. And by the time we're actually done validating, in a sense, we've moved very far away from the primary business process. So then making this step back is going to be challenging in many situations. And adding to this, there's also very different requirements that you would have when training a model versus when deploying a model. So in a sense, in training, you would like to have access to all the data available. You want to quickly iterate over multiple models. You want to do predictions for pretty much all of your data set. And in some ways, you want to just be, have ease of use in developing your models. Whereas in deployment, the situation is quite different. You're often facing just a single data point at a time that you need to do inferences for. You want those inferences to be fast. You want them to happen reliably and at scale in the environment that you're actually deploying in. So in a sense here, you would have performance and portability over the ease of use that you would like to have in training. Clearly, some people are already kind of bridging this gap from the training environment to the production environment, as I would call it, for specific models. So it's good to look at what people are doing right now before actually talking about how we do this using Scailable. So I think what people are doing right now, by and large, is categorized into three different branches. One is what I would call effectively the containerized as-is solution. So effectively, you take all of the code and pretty much the model as you developed it in training, and you just move it to a separate instance. You wrap it in a large container that now can execute pretty much all of your training code wherever you want to run it, which is often in kind of a cloud type of solution. So this is the containerized as-is solution, which is relatively simple to do because you just move what you had to a large container and kind of it runs as is. But it is inherently extremely slow by the container being very bloated. It contains the runtime for all of your training stuff that you don't need. And very often it's hard to move these containers around to various deployment environments. So it doesn't actually satisfy all of the requirements you would have in a deployment situation. An alternative, which is kind of the other end in some ways of the spectrum from usability to performance, is you take a model and you strip it of everything that you don't need. So if we're talking, for example, about a simple regression model, you remove all of the code that was used for fitting, all of the code that is kind of specifying how good the model performs, and you just retain the few parameters and kind of the model formula that you need. You rebuild this in a lower level programming language. So in effect, you end up with an executable that carries out your inference test, this specific inference test, as fast as possible. Now, that is highly performant and can be made pretty portable as well. However, it's a very cumbersome process. So here, in a sense, you've given up all the ease of use of deployment in favor of performance. There's also this third branch that I see a lot with large companies that need really quick inferences. Effectively, what they do is they generate a lot of the inferences offline. So they evaluate their model, often in kind of the training environment, loads of times offline, so not at the moment that the inferences are actually needed, and just store for as many as possible values of the feature vector the predicted outcomes, which then means that by the time you need to make an inference, you only need a database lookup. So that's very fast, but it obviously only covers relatively small feature spaces. At the alternative that Scailable actually provides, it's good to somewhat understand what makes inferences performant. So given that you have fitted a model, how can you very quickly and reliably generate inferences from it? And some things that make inferences performant are just, in a sense, very basic computing science ideas where ease of use is kind of traded off with performance. So moving, for example, to a lower level language where your variables are strongly typed, where the compiler can actually do a lot of optimization, often greatly increases speed. So moving from your standard Python or R stack, which is interfacing with C or various other lower level applications, to actually implementing all of that process in some kind of lower level language often speeds up inferences quite a bit. And in that same vein, actively managing the memory that's being used by the process often speeds things up as well. So here it's just the more, in a sense, we do and the compiler does, the less the computer needs to do at runtime when it's actually generating these inferences. Now, these are in a sense straightforward things that make inferences fast or just make computing fast. But really what's happening and what's even more important when generating inferences is that often the whole process is tremendously slowed down by what I would say the number of layers that need to be passed before inferences are actually generated. So especially if you think about this containerized as is solution, well, you would have some data coming in through like a REST API call that's then forwarded from the operating system to a virtual machine that's actually running the container, to Python, which is then interfacing with C, where the actual inferences are done. Often this goes back and forth multiple times, and all of these layers in and out are going to consume overhead and time. So in a sense, this really kind of highlights why this first solution of containerizing as is, although it's relatively easy, is actually not performant at all. Let's have a look at how we try to solve this whole problem of moving machine learning models reliably and quickly into production. We're actually using a slightly different approach, which in some ways you can think of reaping the benefits of both ease of use as well as performance. So what we do is we enable data scientists to fit models whatever way they want. For example, using their Python stack, using scikit-learn, PyTorch, whatever tools they would like to use. So we're not moving out of kind of the ease of use ecosystem. However, by using one package, the Scailable Pipe package, once you've fitted your model or pipeline, you can upload that saved kind of object to our servers. And what we will do is effectively will automatically transpile that model to WebAssembly. So what does that mean? Well, a lot of things are actually happening. We'll get rid of all the stuff we don't need for the inferences. So we'll, again, if we're talking about this regression context, only retain the parameters and the model formula that are necessary. Then, given this very small description of the inference task, we now automatically move it to WebAssembly, which is strongly typed, memory managed. It's actually a super fast compile target. And from there, once you have your specific inference task available in WebAssembly, so now in a sense, you've automated the rebuilding in a lower level language process, you can now run this model pretty much anywhere with very little layers. So the WebAssembly runtime is extremely efficient. You don't need all the large containers. You don't need all the interfacing. You effectively now have ease of use to generate a highly performant model instance or executable that can be run pretty much anywhere. Just to understand effectively where this speed increase actually comes from, like one of the main things is like this stripping of all of these layers. And then it's good to understand how much increase kind of in speed and in memory you would actually get. And here is just a simple comparison of running an R-BART model, so Bayesian additive regression trees, in a Docker container versus transpiling it to WebAssembly and running it on the Scailable platform. Effectively, the memory footprint is decimated. It's just like more than 10 times smaller. And the evaluation time of generating 1,000 draws from the posterior of this model, so this is a Bayesian model, is much, much smaller than it was in kind of the original containerized as is solution. So stripping all these layers and actually moving things down to a much more lower level language really does improve the performance. Just the performance increases that are interesting. One of the main things, or one of our main reasons of choosing WebAssembly as a compile target for machine learning models is the fact that these WebAssembly binaries can effectively be ran everywhere. So now if you think back to our original problem of deploying machine learning models in hospitals, we now have a solution where instead of sending out data that's generated in the hospital to some cloud service through REST APIs, where it's very hard to control where this data is going and to maintain privacy, we are now faced with the opportunity to send this model directly to the hospital. Because we've compiled a model as a very small standalone runtime or a standalone executable that can run in an extremely small runtime, we can now make sure that these models are being executed at the hospital without the data ever leaving the hospital. Showing a demo of how all of this actually fits together, it's good to think a bit about, or to reflect a bit about what this WebAssembly thing actually is. I've been talking about WebAssembly as this kind of really fast, small packages for running these models, but what is WebAssembly exactly? Well, WebAssembly effectively came about over 2 years ago and was initially conceived as a way of speeding up execution of various processes in the browser. It was actually conceived as a sped up version in some ways, or at least a way in which you could offload some processes from JavaScript to a much faster kind of runtime or a much faster execution environment. And it is by now really an accepted standard. It executes at native speed, and it's actually very safe and sandbox. So it's this really cool kind of standard of, in some ways, wrapping processes. However, the name WebAssembly in some ways is deceptive because it implies that it's just intended to run on the web, which definitely is not true. WebAssembly actually runs obviously on modern browsers, but you can have runtimes available in virtually all languages. And so you can have server-side solutions that run WebAssembly very efficiently in very small containers. And even more so, we have WebAssembly runtimes for various very small IoT devices. So kind of on top of being able to send models, for example, to the hospital, we can actually send models to drones, to cameras, to all kinds of devices where normally you would have a very hard time deploying models to. By using WebAssembly, models are now extremely flexible to move around. And a very large ecosystem of tools to compile to WebAssembly actually exists. So you can effectively generate your own WebAssembly binaries. What we do as Scailable is just make it very easy to take a lot of standard models in AI and machine learning and port those to WebAssembly without you having to worry about this conversion process. The only thing, obviously, is that if you want to run on the Scailable platform with your WebAssembly, you will need a bit of standardized I/O to the binary. All of this is very well detailed in our documentation. So if you want to make your own WebAssemblies and not use in some ways our Scailable pipe package or all of our automated tools to upload and convert models to WebAssembly, you can actually just use your own, upload them, and use them in our runtimes on our servers pretty much everywhere. Let's look at a small demo of the usage of Scailable. You can use Scailable directly from your Python workspace by installing the Scailable pipe package. After training a machine learning model, using for example scikit-learn, you can use Scailable to make your model extremely efficient and deploy it. To make your model inferences efficient, simply use the upload function in the Scailable pipe package. You will have to provide the fitted model object, an example feature vector, and a documentation for the current model. After providing your Scailable account details, the model will be sent to our toolchains and we will automatically convert it to a safe, fast, and efficient WebAssembly executable. We will make your model available for you as a REST endpoint. You can view all of your available endpoints by using the endpoints function in the Scailable pipe package. You can directly use the printed link to generate inferences. Scailable makes it easy to integrate your model into any application. You can simply copy and paste the code to integrate. For example, you can use curl directly to generate inferences. By logging into admin.scailable.net, you can administer all of your created endpoints. Here you will be able to edit the endpoint docs and download the WebAssembly binary in case you would like to host your model on your own servers. That's it. Fast and highly performant deployment of AI and ML models using WebAssembly. Get started at www.scailable.net. I want to close off this talk with discussing a bit of where we're going with Scailable, where's the product heading, and also providing you some resources to get started. So let's first look at our roadmap. We've now looked at some of the main kind of functionality of Scailable, very simple, quick transpiling of fitted models to WebAssembly and then deploying them anywhere. But it's good to understand where we are with the product and where we're going. And really right now, we're out of the box supporting all of scikit-learn, stats models, XGBoost, and converting all of that to WebAssembly. We are currently also supporting all of ONNX and porting this to WebAssembly, although ONNX is right now available from our web admin, not from the Scailable pipe package, but we'll include it as soon as possible. With this full ONNX support, effectively, we're supporting TensorFlow, PyTorch, and pretty much any model class you can think of. It provides a very flexible framework of moving fitted models into WebAssembly. That's on the compiling end. On the other end, though, we're also heavily invested in making more runtimes and kind of extending where we can run. So if you upload your model through the Scailable pipe package, we will automatically deploy it on our cloud, which means you can run it just using it as a REST service. But we can obviously also deploy this on-premise in your company or wherever you want it to run. And currently, although it's kind of not available freely in our beta, we also have runtimes for the browser, running specifically the Scailable WebAssembly packages in the browser as fast and as small as possible, as well as runtimes for various IoT devices. And we're effectively just extending the range of runtimes that we have to make sure that we can really deploy instantly anywhere. One other future plan that we think is super cool, a lot of people don't necessarily think it's cool, but we think it's fun, is that we're actually developing a unikernel runtime for scalable WebAssembly packages, thus really stripping all of the layers that we can strip and making this as fast as possible. So that's where we're heading. We're basically just increasing the number of models that can easily be transpiled to WebAssembly. We're increasing the number of runtimes. We're just making this as easy as possible. We'll be working on monitoring and experimenting with models as well. So there's really a lot of cool stuff coming up. If you're interested, after looking at this talk, in kind of trying out Scailable, in looking at some of our resources, I would say the easiest way to get started is just go to scalable.net, sign up, and we'll try to kind of validate your account as quickly as possible, and you can start, just give it a spin, try it out, see if it's useful for you. However, you can also check out all of our resources, all of our materials. We have a lot of tutorials to get people going. We have a number of different demos that are up. If you go to Scailable tutorials, you'll find all of those demos as well. So there's a lot of material to get you started and use the product as quickly as possible. If you have any questions, send an issue in our Git or just send us an email. That's really it for today. Thank you so much for listening.
Thanks for watching. I hope you enjoy using Scailable, and we'll hope to see you soon. Thanks. Bye.